Okay, so now that we know a little bit about the history and the origin of the periodic table, we're just going to take some time to work on the vocabulary and the words that we use to talk about it. So, the rows in the periodic table are called periods. So the red with hydrogen and helium is a period, the orange row, the yellow row, and those are the rows that are really organized by increasing atomic number, right? So now that we know the atomic numbers, we can use those. And what we find is that it's usually consistent with the atomic mass that Mendeleev used, but not always, especially in the transition metals. You know, those guys are kind of high maintenance. There's some places where there's just an atom that randomly has a bajillion neutrons and weighs more than its neighbors, but it's fine. So here's our periods. That's how we talk about the rows. And then we use the word family or group to talk about the columns. The patterns in the lanthanides and actinides and the transition metals are a lot more subtle. And because there's kind of more things in play right there. If you think back to the electron orbital diagrams and you think about how close the D and F orbitals are like squished together up there, like it's just kind of chaos. So we can't necessarily talk about the patterns as strongly, but these vertical columns in the S and P block have some really elegant patterns in them that are really helpful for us to talk about. So these families or groups have similar chemical and physical properties. For example, you know, every noble gas, this kind of light teal, those guys are, I mean, they're gases, right? That's why they're called noble gases, is they're gas. They all act the same. These purple guys, these are the halogens, they all act the same. We'll label your periodic table with the names of the families in a moment, but these red alkali metals act the same. The orange alkaline earth metals act the same as each other. It's pretty cool. And that, you know, that's what Mendeleev used to organize the table, was this idea of like, whoa, all these things act the same way. They must be a family. I don't know. I don't necessarily act like everybody in my family, but it's a sweet idea. A little family of elements. So let's think for a minute, put on our electron configuration hats. Why might elements in a family have similar chemical and physical properties? So hopefully you're starting to remember the other like rainbow colored periodic table I showed you that showed that if you're in the same column, you're in the same group, you have the same electron configuration ending. So all of these red ones, they all end in S1. All the orange ones end in S2. All the yellow ones end in P1. All the green ones end in P2, and so on and so forth. And that's why they act the same, is because the electrons, which do all the chemistry, look the same from the outside. And so that causes them to act in a really similar manner. So here's my favorite example because it involves explosions. All the metals in the first group, so the alkali metals, they all act really, react violently with water. So while you watch this video, I want you to think about a couple things. Consider the electron configurations of lithium, sodium, potassium, and rubidium. Why do you think these all react the same way? And why do you think they have such a violent reaction?
want your treats? Come here. Come here. You want to sit? I'm a good girl. Okay, go.
All right, best quote of that entire thing. You can see that things gradually become more terrifying as we go down the group. Like, thank you, Captain Obvious. That was awesome. So, why do these things all react in the same way? And he talks about this kind of in the video, right? They all end in that S1. And we kind of know that elements like to have full energy levels if they can, or full orbitals if they can't get to a full energy level. Like they'll try to get a full sublevel instead. So these little guys, lithium and sodium and so on, they're like, hey, if I just throw away an electron, I could have a full energy level from the level kind of below me. So they just throw away their electron, and that's why they react so violently. And as they go down the table, they become more and more violent because the little inside of the atom is farther away, right? So the protons, the magnet that attract the electrons, is farther away because you're getting bigger and bigger, and we'll talk about that. But it's really an interesting set of patterns in that family, and it kind of starts to make sense with the electron configurations. So take a sec, pause the video, color code your periodic table using the system below. So these families that are shown in the middle, okay, so alkali metals, alkaline earth metals, lanthanides, actinides, transition metals, post-transition metals, metalloids. Metalloids are cool because they kind of act like metals, they kind of act like nonmetals. Sometimes people call them semi-metals. They're pretty cool. They're in this pink. It can be hard to tell it apart from the gray, but it's the pink. And then we have the very nondescript other nonmetals. Those are the ones that do a lot of biology, are these bright blue ones. And then we've got the halogens, which are very reactive also. And because of that, they're pretty toxic. And then we've got our macaroni orange noble gases, and the noble gases don't react with anything because they already have a full P sublevel, and they're like, psh, I don't need your electrons. So they're very stable. And they're called the noble gases, right? Because they don't react, they don't associate with the riffraff of the other elements. So they're like the kings of the elements, kind of, or the queens. Okay, so the other thing we can record patterns-wise is the valence electrons in each family are going to be the same. So group 1 are alkali metals. They all have 1 valence electron. Group 2, the alkaline earth metals, they all have 2 valence electrons. Then we've got this third group with boron at the top. that has 3 valence electrons. Carbon's family has 4 valence electrons. Nitrogen's family has 5. Oxygen's family has 6. The halogens have 7. And then the noble gases have 8. Some people say they have 0 valence electrons because they have a full energy level. I usually say they have 8 valence electrons because when we start really talking about bonding and like why bonding happens, the reason is that everybody wants to have 8 electrons in their outermost energy level. Right? They want to have an octet. And so that makes more sense to me to say they have 8 valence electrons because everybody wants to be like them because they want to have that octet. But anyway, either way, it's kind of the same idea. So record those. The other pattern that is useful to remember on top of there is the most probable charge. So are they likely to gain or lose an electron? Again, totally based on the configuration. If you have one little dingleberry electron, then it's probably just going to get taken away. Right? And that's what happens for our alkali metals and somewhat violently, as we saw in that video. And then beryllium's family, they usually have a 2+ charge. Boron and its family usually is 3+. Carbon just like its family just doesn't really have charges. At least the first two definitely don't. Sometimes germanium does, and then tin and lead act more like metals, so they'll get a positive charge. But these guys, they just don't really want to give away 4 electrons or get 4 electrons. It's like a lot of work, so they usually just keep their electrons. Kind of the same with nitrogen and phosphorus. You don't see a ton of ions forming from that family. And then the oxygen's family, that'll form some ions, some 2- ions, and then the halogens form 1- ions. Quite a lot, because they like to gain an extra electron, because then they're over here looking like the noble gases. Noble gases, of course, have no charge, and because they don't need to gain or lose electrons in order to be stable. One thing to note, y'all, is that anything that's a metal can only have a positive charge. Metals just give away electrons. They never gain electrons. They just don't. So even if they're in a family that says, oh, they have a 3- charge, that's really only referring to the nonmetals, because by the time you're talking about bismuth or lead or tin, those guys act like metals, so they only ever have a positive charge. So just something to keep in mind. Yeah, anything that's a full-on metal is gonna have only a positive charge. So periodic table, it's a beautiful study in patterns. There's many useful patterns on the periodic table. We call them periodic trends, and they help us think later on. They really help us think about why atoms are acting the way they are, why bonding is happening the way it is. And so we're going to take some time to explore those as well. So I'm going to go ahead and cut this video off here. There'll be a 3rd installment, and we'll chat about the periodic trends.